And let's go. Let me share my screen.
Just double checking
Yeah.
because, like, going to print it, it says it's due Friday. It's definitely due Monday, right?
Where does it? Oh, it says on the
At
actual
the
test
top.
it's due Friday.
Yeah.
Yeah, just ignore that.
Okay.
It's due
Thank you.
Monday. Yeah, it's use the Moodle when it says it's due on Moodle, right? It says the right date on Moodle. Yeah.
Uh, Probably.
Yeah.
I'm not looking at it at the moment.
Let me double check.
I have too many tabs open and it's very hard to navigate.
Yeah. I hear you. Yeah. 10/12 is when it says on.
Yeah, I see that now. My bad.
Ignore the one on the paper because it compiles it. You know when I just didn't recompile it. Do you know what I mean?
Gotcha. Yeah, that's fine. Thank you.
Sure. All right. Let me share screen. Oops. Sorry. Okay. So this is where we're at last time. Just to remind you, we were looking at sort of the inverse transform up here. If you can see right up here, right? We were looking at here's the transform that goes from the unrotated to the rotated, or from one basis to another basis, right? Same idea. And then this is the one that goes back. There's a fly in here. So in other words, like if you had the Vij primes, or sorry, the Vj primes, then you want to get back to the unrotated, right? Or if you had basis B and you want to get to basis A, this is what it would look like, right? And we were looking at uh, the fact that these must be inverses of each other, right? Because we basically just substituted in, and we know that this thing here, this Aijbjk, is matrix multiplication. We explained that down here, right? That it is actually matrix multiplication, and we called that thing C, right? A matrix multiplied by a B, and that was our CIK, right? So the elements of the matrix here are given by these elements multiplied together, right? And then we said, well, it has to be delta IK, and we explained what delta IK is, right? It's the identity matrix, or elements of the identity matrix, right? With the rules that if the indices are the same, you get 1, and if the indices are different, you get 0, right? Yeah. Okay. All right, so let's keep going on this, just trying to understand this index, what we call index gymnastics, right? Dealing with the Einstein sum convention, dealing with the indices for things. Okay, so remember that we also stated, I'm going to get a new layer now, okay? Because I don't have any room on this one. Okay, move this over again. Let me move some of this stuff around because well, you can't see some of the stuff, but I can. And it's annoying me. Okay. Let me see if I can get this to move up here. Give me a second. Meow, come on. No. Okay. Maybe I can make it smaller. Sorry, give me 1 second, try to optimize this. It's weird that I can't really move this window around. Okay, whatever, I guess. It's the best I got. Alright. Move this guy down. Alright. Give me a second. All right. All right. So remember, we said that a while back. We said that the aij's, right? So remember, our equation is vi prime is given by this Aij Vj, right? So this could be, you know, matrix, this could be the components with respect to basis B and how they relate to basis A, or it could be the components are rotated by some angle related to the unrotated coordinates, right? And this translates to this matrix operation, right? Where this, if we're in, if V is a two-dimensional vector, this would be a 2 by 2. If V is a three-dimensional vector, this would be a 3 by 3. If V is a 11-dimensional vector, this would be an 11 by 11, right? A. Okay, so that translates to that. All right. And then we said that the Aij have several different, for rotations, right? So for rotations, right? These are the direction cosines. Which mean that it's the cosine of the angle between x prime I, and I always get this backwards. I always gotta go and double check. Yeah. X prime I, x j. So in other words, the cosine of the angle between this guy and this guy. Okay, that's what the Aij's are. But we also said that they were these partial derivatives. Partial x prime I, partial x j. Right? That's what we said. Okay, so what about the B's, right? We said, before we said the Bij's, and let's go over here and put that down. That's the B I is equal to Bij Vj prime, which of course translates to V is equal to the matrix B times V prime vector, right? Again, this is a 2 by 2 vector. V is a two-dimensional, etc., right? Okay, and that these guys for rotations are the direction cosines between the x unprime I and the x prime j, like this. So you can see it's kind of the backwards, right? And then now these are the partial derivatives with the unprimed on the top and the primed on the bottom. Okay. All right. So this is just, we haven't proven this or anything, but we're just showing you that that's what these are. Okay. So you can see that they're opposite these, right? So these have the x prime on the top and the unprimed on the bottom. These have the unprimed on the top and the primed on the bottom, right? Give me a second. Okay. Oh, it did go to the top. Okay. Sorry, I'm having issues with my screen. It's not working right. All right, let's see if I put you guys at the bottom, if that'll work. All right. You guys can't see yourselves on my screen, right? No. Okay. So hopefully that won't interfere with anything if I move it somewhere. It won't like cover up any writing or anything. Okay, good. All right. Okay, fine. Okay, good. So now, and then we said we have, you know, when we did this, we said, oh yeah, look, what if we do V prime I is A I J V J, and now we replace our VJ with this guy, right? Then that's going to be A I J and then B J K V K prime, and that's where we got that this has to be delta, right? I K. But let's write that down in terms of the partial derivatives now. So we're going to put our Aij, so partial x prime I partial xj. And now for the b, jk's, we're going to say partial xj, whoa, partial x prime k, right? vk prime. Okay, so let's take a look at this. Now, by the rules of derivatives, right, you can see that this partial xj here and the partial xj here are going to sort of cancel each other out, right? You know, it's kind of like if you have chain rule or something, right? You have like, you know, df, dx, dx, dt, and they're like, oh yeah, this is just df, dt, right? Right? So, same thing here. These guys are kind of cancel each other out, and we'll have partial x prime I partial x prime k vk prime, right? And if you notice here, this is, think of it like, remember that the i's are like, let's say for two-dimensional vectors, it would be, you know, partial x partial y. Well, okay, let's write it out. So let's just write out for I equal 1 and k equal 1. We'd have partial x prime 1 partial x prime 1, which translates to partial x, right? Which I hope you agree, that's 1. And if we do x on I equal 1, k equals 0, oh, sorry, 2, k equal 2, we do partial x prime 1, partial x prime 2, and that would translate to partial x partial y, and there is no partial x partial y, right? That's 0. Does that make sense? Oh, sorry, prime. I'm leaving the primes off. I'm so sorry. There we go. So this one was partial x prime, partial x prime. This is partial x prime, partial y prime. Right? And remember the x primes are like, you know, x cosine phi plus y sine phi. Right? They don't depend on the primed coordinates. They depend on the unprimed. So when you do this, you're like, well, that doesn't, right? X prime doesn't have a y prime in it, so that's going to be 0, right? And again, you know, if we go vice versa, right? I equal 2, k equal 1, partial x prime 2, partial x prime 1, and that's going to be partial y prime, partial x prime. And remember, y prime is, I think, minus x sine phi plus y cosine phi. I hope I'm not making that up, but something like that. There's no primes over here, right? So that's 0. And of course, I equal 2, k equal 2, partial x prime 2, partial x prime 2, which translates to partial y prime, partial y prime, right? Which is just 1. Okay, so again, this thing here is delta ik, the identity matrix, right? Or the elements of the identity matrix. And remember what we said delta does, it changes all k's to I. That's what it does. So you can get rid of this by just saying, oh, well, this just changes all k's to I, and I get v prime I. And notice v prime I is what I have over here, right? Does this make sense to you? Hopefully? Maybe? Okay. All right. Let's look at some more. So we're kind of going to leave our transformations for a second to just do more index gymnastics things. And I'm going to get a new layer since we got to kind of start a kind of longer thing up, and I don't want to run out of room. So I'm getting a new layer. Okay. Move it out of the way. Okay. All right. So let's look at something like trace A transpose B. Now this, where A and B are matrices, this was the inner product of for an inner product built for a matrix vector space, like say the vector space of all 2 by 2 matrices. Right? So we want to look at, does trace A transpose B equal trace, does it equal B transpose A? Okay? And where these again are matrices. And we're going to do this using our index gymnastics. Okay. So first, we're going to see, prove this. So first, we're going to prove trace A. Does trace A equal trace of A transpose? Okay, we're going to try to figure that out first. Okay. All right. Well, we're going to do this with index gymnastics. We're not just going to make up some matrix of some dimension. We're going to do it in a very general way. And so when we write down A, right, if we write down A transpose, we want to write down the elements. So an element of A transpose, we write it like this, right? So what does that mean? Let's look at a concrete example. So we have A, let's just say it's 2 by 2. Right? We'd have, 1, 4, 5, 2, right? So A transpose, remember, is that you flip over the diagonal. So it'd be 1, 5, 4, 2, right? That's A transpose. Okay, this IJ just means an element of this, of the A transpose matrix. Okay, so if I is 1 and J is 1, it would be A transpose 1, 1, which would be the 1. If I was 1 and J was 2, that would be A transpose 1, 2, which would be the 5. So this is an element, right? So whenever we work with indices on matrices, we're working with elements on their own. It's almost like it's not a matrix anymore, right? It's an element of a matrix, one of the elements. Yeah, it has IJ, can be any one of them, right? Depending on how you choose I and J. But this is just one element. Okay, just to be clear on that. Now, if I take this and I want to get rid of that transpose sign, I can say this is equal to A, J, I. Okay? Notice what I did here. I got rid of the transpose sign and I switched J and I. So why did I do that? Well, let's take a look. So if I say A transpose IJ, right? Let's look at J equal 1, and sorry, I equal 1, J equal 2. Okay, I'm going to start with that. And A transpose 1, 2 is 5, right? But here I'm saying, hey, I got to switch these indices, right, to make it just A. So let's look at A, where J is 2. Sorry, I didn't want that parenthesis thing there. Okay. I wanted it like this. A, where J is 2 and I is 1. Okay. So A 2, 1 is this guy, 5. Right? So notice that I have to change J and I like this to get this equality. Otherwise it would be switched, right? Otherwise, if I didn't switch J and I, then I would be saying that A transpose, 1, 2 is A 1, 2. Well, that's clearly not true because A 1, 2 is 4 and A transpose 1, 2 is 5, right? So I have to switch them when I take away the transpose sign. And of course, if I want to go backwards, if I want to, put the transpose sign back on, I gotta switch them again, right? Is that clear? Okay. All right, but we're trying to figure out this here. So we're going to do the trace. We haven't done anything. All we're doing here is showing you that the transpose sign means you got to switch those indices. Otherwise, you won't have a true statement, right? Okay, so we're looking at this right here. We're trying to prove this guy. All right, so we know that the trace is the sum of the diagonal elements of a matrix, okay? So I can write the trace of a matrix literally by just saying, so trace of A is A, I. Remember that repeated indices are summed over, okay? So this is shorthand for A11 plus A22 plus A33 if it's a 3 by 3 plus A blah blah 4 4 blah blah blah, right? How many dimensions you have, right? In our case, our little example up here, of course, we wouldn't have A33 and A44. We would just have A11 and A22. So a trace is you write like this, right? Remember the Einstein sum convention, right? Okay. All right. So I'm going to come over here and I'm going to start with AII. That's my trace. So trace A equals AII. And then I'm going to come over here and start trace A transpose, right? Well, what is that, of course? Well, it's A transpose I, right? That's what that is. Because A transpose is the matrix. Remember, it's a different matrix than A. It's up here, right? Here's A and here's A transpose. So A transpose II is that's what the trace is. But notice if I want to take the trace off, I have to switch the two indices. Well, they happen to be the same. So it's going to look exactly like that. And therefore, that's equal to trace A. Right? So we just proved what we need to prove, which was this. So, yeah.
Okay, you may have already gone over this when we were going over the transpose trace thing. Is there, because in a transpose, the only thing that's not being affected is the diagonal.
Yeah.
So is there even a reason to transpose it?
What do you mean a reason?
Like, if...
I think he means because the community property of addition. Am I right, Jackson?
Yeah, because... like... Sorry, there's a gnat in here. There's... By my logic, the trace of A and B will equal the same thing as the trace of the transpose A and B.
I'm sorry, I didn't get what you said.
Oh wait, you have to multiply it before transpose it. Okay, never mind.
Okay, I see what you're saying. Yeah, I got you. Yeah, no, it's the multiplication thing.
Yeah.
Right? Otherwise, it would be, because we just showed that, right, trace of A is trace of A transpose, because just what you said, right? Nothing changes along the diagonal, right? We just showed that here. But we need to do that multiplication stuff in there first, right, to do that. Okay, so let's move on to our bigger target. Let's write down an equation for this. We're going to start with A transpose B. So we have A transpose B, and I'm just for simplicity going to call that C. Okay, so that's the matrix C. Okay, and we're gonna just for an example, we don't have to say what the dimensions are, but we could just say that A and B are, two by twos, just for fun, right? And so we know that if it's the 2 by 2, right? So if we use our A like we have over here, and let's use B equal, 0, 1, 2, 1 or something. I'm just making stuff up here. Then, if we do A transpose B in matrix multiplication, right, that's going to be 1, 5, 4, 2, matrix multiplied by 0, 1, 2, 1, and that's going to be, row times column. So let's see, 1 times 0 plus 5 times 2, that's 10. 1 times 1 times 5 plus 5 times 1, that's 6. 4 times 0 plus 2 times 2, that's 4. 4 times 1 plus 2 times 1, right? That's 6, right? Am I got that right? Pretty much. Please check the algebra. I'm bad with the arithmetics. Okay, right? So it's a 2 by 2 matrix C. Yeah, we could have said that. We didn't need to do all that. Just to point out that the way that the dimensions work, right? So it's 2 by 2 matrix multiplied by 2 by 2, and this inner thing here, right, is 2, and this is 2. They just need to match, which they do, and you can kind of think of them canceling out, and you know you're going to get a 2 by 2 in the end, okay, without doing this little exercise. Okay, anyway, it's a 2 by 2 matrix. So I'm going to write down one of the elements of C, Cij, right? So in other words, if I is 1 and j is 2, it's going to be 6, right? For 1, 2, it'll be 6. For 1, 1, it'll be 10, right? For 2, 1, it'll be 4, right? Etc. It's just an element, one element, okay? And of course, I can now write this and just put my little parentheses around and say, well, of course, that's an element of this multiplication, right? Isn't it? Okay. All right. So now I know in here that this is matrix multiplication, right? Okay, so so I need to figure out how to write that in indices. So remember that we've done this already, right? When we have two matrices, let's say, you know, D matrix times E matrix, right? That if we want to write the elements of that if we want to write matrix multiplication, that's D, I, J, E, J, K, right? These inner things need to match. That's what's summed over, right? We proved that in the previous layer, right? So if I want to write out what this is, right? And so now this, let me be clear here. This would be IK, right? This is the element of this matrix multiplication. IK would be this, because the free indices are the I's and then the K, right? On this thing. Okay, so here I've got to write that out. So I'm going to say, okay, it's A transpose. I need the free index to be I, so the first index needs to be I. I'm going to leave the second index blank because I'm going to write down B. The matrix B, I need the free index to be J, so that's to be over here. And then I just need a couple of dummy indices, and I'll just choose K. So K is summed over here, and this is matrix multiplication now, right? And the two free indices I or J match the ones over here and the ones here, and that's good. Okay, following me so far? Okay. All right. Now I know that a transpose, if I wanted to convert it to A, because look what I'm trying to prove, right? I'm trying to prove way up here, I'm trying to prove that this guy, the trace of this is equal to the trace of this, right? So I've got to kind of move things around. So I'm gonna get rid of the trace on, I'm gonna get rid of the transpose on this. I know how to do that already. I can just switch the indices. So A, K, I, B, K, J, right? And now I want to point out to you that this is not, I cannot write a matrix multiplied by B, right? That is not true here. So someone tell me why that is not the case.
Because it's different indices?
What do you, be specific?
They're not summed over the same, right?
They're not what?
Do they not have, like, they're not summed over the same thing?
Okay, well the K is still summed over, but what's wrong with that?
It's in the wrong position.
It's in the wrong position. That's right. Absolutely. How could I make it in the, well, okay, there's two steps to making it into the right position. one step is moving B, right? So let's do that. We're going to move B. Now, why can I do that? Okay, I know that somewhere, you probably remember that you can't just take matrices and they're not commutative, right? So if you take two matrices A, B, A dot B, right, with matrix multiplication, that is in general not B dot A, right? B matrix multiplied by A, generally not the case, right? They don't commute. That's how matrix multiplication works. Okay, so but these, when I can move B, because literally it's just one element of B, right? It's just a number like, 5 or 10, 10 or 6 or 4, right? Or sorry, no, that's not B. This is B. 0, 1, 2, or 1, right? It's one of those. It's just a number. So I can move it. That's the power of these index working with indices. You're working with just one element. You're not working with this big matrix thing that doesn't commute, blah, blah, blah. Okay, so we've got one step down. But here, here you can see, like, if the K was just over here in the J spot, I would have matrix multiplication, right? So how do I get it? How do I get the K into the J spot? And the J into the K spot?
Transpose B.
Yep. So B transpose J K A K I. And now, right, I have matrix multiplication, right? But if you look, right, this is now C transpose, isn't it? Because look, this is C J I. Look at IJ, JI, which is in fact C transpose, right? IJ.
And also the transpose of a matrix is equal to its original.
Right. Fine, but we're not actually trying to prove that, right? We're trying to show that the trace is equal. Let's go back. Okay. So what we're gonna do is we're gonna write down.
I mean the trace. I'm sorry.
Right. So if you look, right. So now my pen is not working. Hello, pen. Wow. Okay. I'm having a little problem. There we go. All right. So remember that we're trying to prove that the trace of this is the trace of this, right? Okay. So let's go back up to here and notice that the trace of this whole thing, right? The trace of A transpose B, right, is equal to A transpose B I, right? So over here, I know what that is now. It's B transpose I K A K I, right? Yeah? Which of course is the trace of B transpose A. Yeah, and then we've proved it. That makes sense? This takes a little getting used to. So remember, this is an inner product, right? This thing here was the inner product for a space of 2 by 2 matrices, or any n by n matrices, in fact. And we showed that that's good. But there's, of course, the usual inner product that we have in 115, right? So let's get another layer and move on to that. Okay, so let's just look at the inner product. So remember that the usual inner product for 115 vectors, right, is the one that you all know and love, right? You just take the components and multiply them together. But it's called a scalar product for a reason, right? Because it ends up with a scalar. And if we have two vectors, A and B, right, then we take A dot B, right, in the notation of 115, or in the notation of this class, it would look like A inner product B, right? And that is A I B I using the Einstein sum convention, right? Where, like, you know, I is 1, 2, 3 in 3 dimensions, and I equal 1 is X, and I equal 2 is Y, and I equal 3 is Z, right? And it's a scalar product because, because it transforms in a particular way under rotations. So remember that a definition of a 115 vector, the new definition, is that it transforms in a particular way under rotations, right? And that particular way is, you know, A prime in a rotated coordinate system is, I'm now using A's, and I probably shouldn't because I was using that for our matrices before, but let's see, let's go. V prime, right, is some matrix that transforms it from the unrotated coordinate system. Okay, and if we write that in components, V prime I is A I J V J, right? Where, of course, we're Einstein sum convention on the J. We just saw this a bunch of times, right? And where the going backwards, VI is the BI J VJ prime, etc., right? Okay, so now this is called a scalar product because now when we rotate, so now what we're going to do is we're going to rotate these two vectors. And actually, I'm going to I'm gonna go back to another notation because I shouldn't have used A and B. So I'm going to use V and W just because it's annoying that to have A's floating around. So I'm going to use, V inner product with W, right? Or this notation that we've been using in this class is this, V I WI, right? For 115 vectors. Okay, so we'll start from here. So let's rotate them. So we're going to do V prime inner product with W prime. So now they're both in the rotated coordinate system. Again, that's in our notation in this class, looks like this. And let's see what happens when we rotate, okay? So I know that this is in components, or and using the Einstein sum convention, V prime I, W prime I, right? Summed over I. And now I'm going to replace them with their rotated, right? With the equation that shows how these vector components change when you rotate, okay? So I'm going to say, all right, so this is going to be A, I, J, V, J. And then this guy has to be I, right? Has to be I, and then K, V, K, right? Has to be I to match the I here, okay? Right? So we have summed over J here, summed over K here, and summed over I. Yeah? Okay, so let's now the beauty of working in components is that you can move stuff around at your will, okay, because they're just numbers, okay? So I'm going to write A, I, J, A, I, K, V, J, V, K. Oh, sorry, bad. This is supposed to be W, okay? This is supposed to be W. Okay, there we go. Okay, All right. And notice here that I don't have matrix multiplication, so it might be a good idea to make this matrix multiplication. And so I'm going to use the transpose of one of them. So A transpose Ji Aik. Sorry. I don't know why usually what I say I write, and I didn't do that. Aik. So we have matrix multiplication here, right? So this is A transpose A. So this is, you know, the rotation matrix A. Matrix multiplied by A. Right? Yeah? And I don't remember if we actually proved this or not, but the transpose of A is its inverse, right? Do you remember that? Maybe we didn't quite do that. No, I don't remember if we did or not.
So it just come out to 1?
Yeah, so let me just write it down. So A, and just never mind this, right? These are, I'm now talking about matrix A's. This is a rotation matrix. So you have cosine phi minus sine phi. Sorry, not minus, plus sine phi here. Then sine phi, sorry, minus sine phi here, cosine phi. And then A inverse is cosine phi minus sine phi plus sine phi cosine phi. Yeah? So as you notice, A inverse is of course just A transpose. Right? So this is of course just the identity matrix. And sorry, I forgot to write down my V's. V, W, K, B, J, W, K. And now if this is delta J, K, because the free ones are this one and this one, then this is V and this is K, V, J, and W, K. This, remember, changes all J's to K's, or all K's to J's if you'd rather. And so this becomes VK, WK, right? So in other words, it is the same, right? This guy here, notice here, right? Summed over I. So in other words, it would be like Vx prime Wx plus, let's go in 2 dimensions, Vy prime Wy prime, right? And notice that that's equal to this. That ends up being equal to Vx Wx plus Vy Wy. Okay? It's called a scalar product because it doesn't do anything under rotations, right? Scalars don't care that you just rotated their coordinate systems. So if this is, 6, this is going to be 6, right? They don't care, right? Think of a scalar field like the temperature in the room. Does not care if you are measuring with respect to, your walls and floor being there, or you rotate your whole walls and floor by, your coordinate system by, 20 degrees. It doesn't care. You're still going to have the same temperature everywhere. It's a scalar. So a scalar quantity doesn't care about rotation or change of basis or anything, right? So that makes it a scalar, the way that it behaves under rotation, where there are none of these factors, right? So look over here, for the vectors, there's one transformation matrix, right? One transformation matrix. Here, there are none. There's nothing here, right? Nothing. There's no factor, just a 1. Okay? So that's how you tell it's a scalar. When you have one transformation matrix, then you have a vector. 0, you have a scalar. So 0, scalar. One transformation matrix, vector. Now, there are things that have like 2 transformation matrices and 3, etc. These are all different rank tensors. This is second rank and third rank. And in fact, a vector is actually a first rank tensor. And this is 0th rank tensor. Ah, that was a mess, sorry. Okay, so that's what a tensor is. It's basically just a vector or scalar or a matrix, or right, and depending on how the object transforms under rotation tells you the rank, right? So this is little tables. This is the number of transformation matrix. Right? 0 for scalar, 1 for vector, 2 for, second rank tensor, 3 for third rank tensor, ... Okay? Okay. Yeah, so the next thing we're going to do is the cross product. And for our 115 vectors, this is not the cross product that you all know and love is not part of an inner product space or anything, because it's not an inner product. It's what people in math would call an outer product, not an inner product, an outer product. But there's no such thing as, say, outer product spaces or anything like that, right? The cross product is kind of its own unique thing. It's the only time you get to multiply vector by vector, right? Because think of the scalar product. It's the only time you get to multiply vector by vector and get back a vector. Because the scalar product, you multiply vector by vector, but you get back a scalar, right? So the cross product, you get back a vector, so it preserves the vector nature, right, of the product. It's the only kind of thing that happens like that, right? Think about vector spaces. You multiply by scalars. And then if you have an inner product, you get that one, product that gives you a scalar back. So the cross product is a little different. It's an interesting little beast. But we're out of time, so we'll continue this on Friday. Now next week, I don't know if you've noticed, next week we don't have class on Friday, and we don't have class on Monday of the week after that. It's all on Moodle. But today we have class on Friday, we have class on Monday, we have class on Wednesday. We just don't have class Friday, Monday after that. Got it? Okay. It's all on Moodle, just giving you a heads up. All right. Well, we'll see you guys later. Hopefully you'll start working on the test soon. Bye, guys.
Yeah.